Hello. Today, I'd like to introduce end-to-end speech recognition and a service called CLOVA Note. Kida from LINE and Yuhexu from NAVER will present. The speech recognition is the result of joint research and development by the NAVER LINE CLOVA speech team. I'd like to begin. I'll be giving a presentation in two parts today. First, Yuhexu of NAVER will talk about what end-to-end speech recognition is and introduce the functions and achievement of the AI voice recording service CLOVA Note released in Korea, as well as the technology used in the service. Kida from LINE will introduce the result of research and development to speed up E2E speech recognition. First of all, let me introduce the CLOVA speech team. I'd like to introduce myself. My name is Yuhexu. I joined NAVER in September 2017, and I am currently the leader of the CLOVA Speech CLOVA team, in charge of speech recognition for Japanese and foreign languages. My hobbies are studying foreign languages and traveling, but this year it has become difficult for me to travel, so I'm focusing on domestic camping in Korea. As the name suggests, we in the CLOVA speech team are doing R&D on speech recognition. There are two major development methods for speech recognition: conventional DNN, HMM, based and end-to-end. We engaged in R&D of both and apply the appropriate speech recognition engine according to the characteristics of the service. In particular, the conventional DNN HMM-based model is widely used in services such as CLOVA Smart Speaker, Wave, Friends, Desk, etc., and AiCall telephone reservation system. In addition to Korean and Japanese, we are also developing foreign language speech recognizers such as English and researching and developing technology for speaker recognition to know who is speaking. Now, I'd like to talk about what end-to-end speech recognition is. Before I introduce end-to-end speech recognition, I would like to briefly talk about conventional DNN HMM speech recognition. When a speech recognizer receives speech, it actually contains not only the user's speech but also various noise and silence. Therefore, the first step is to detect only the utterance in the speech. It determines where the speech started and when it ended. This is called endpoint detection, or EPD. After EPD, there is a stage called feature extraction, where the speech features are extracted from the physical speech in the form of vectors for each frame. The task of speech recognition is to estimate what kind of string the speech will be from these features. In conventional speech recognition, three models are required. The first is the acoustic model, which shows the relationship between features and the phonemes. Second, the pronunciation model, which shows the relationship between phonemes and words. And the language model, which shows the relationship between words. The three models are combined to produce the most probable text output from speech. This conventional speech recognition technology has its advantages when it comes to patterned speech. For instance, it is relatively easy to improve performance when the content of the speech can be predicted in advance, such as "Tell me about weather in Tokyo today," or "about the weather in Okinawa tomorrow." In addition, when additional measures are needed, the acoustic, language, and pronunciation models can be selected and modified for each component according to the component. And it leads to the advantage of ease of improvement. On the other hand, this advantage is not so effective in the case of so-called free speech, where the content of speech is difficult to predict and pattern, such as in news broadcasts and a daily conversation. End-to-end, so-called E2E speech recognition is advantageous in case of free speech. Now, let's talk about E2E speech recognition. Our E2E speech recognition is called Neural End-to-End Speech Transcriber, or NEST for short. The NEST engine uses a single model for speech recognition, unlike conventional speech recognition, which uses 3 models. In other words, speech recognition is performed with a single model by directly modeling features and text. What are the features of this next model? As mentioned earlier, the strength is in the recognition of free speech that cannot be patterned. It is also robust in noisy environments. Even in the presence of noise, it does not recognize the noise as if it were part of the speech, but recognizes only the content of the speech. Because of these characteristics, NEST is expected to be applied to free speech domains such as subtitling in news broadcasts and taking minutes in meetings. On the other hand, such E2E has some difficulties. It requires unprecedented large amount of data and requires a lot of computation and decoding. Finally, unlike conventional speech recognition, which can be improved on a module-by-module basis, E2E is hard to customize because it possesses everything with one model. Next, I am going to introduce CLOVA Note. What is CLOVA Note? CLOVA Note is a service that records your voice, converts it into text, and keeps it as a record. It can be used in meetings where you need to remember what you have said, and in other situations where you need to check it again later, and interviews where it is difficult to write down everything, and lectures where you want to listen again for reviews. CLOVA Note is very helpful. Recordings that are too difficult to listen to again and have not been summarized can be automatically converted into text so that you can quickly find the information you need. When using CLOVA Note, we ask the user to just record. After that, recognition and analysis of speech contents can be left to us. This voice recording with CLOVA Note is currently being offered in Korea, not only in Korean, but also in Japanese and English. We are planning to expand the service to Japan in the future. I hope you try it at that time. Let's continue to look at the features provided the current release of CLOVA Note. The first feature of CLOVA Note is that it allows you to listen to only the parts you need based on the recognition results. There is also a memo function that allows you to write down important information like a bookmark while you are recording. The memo function allows you to write down important information like a bookmark while you are recording, making it easier to summarize important information in your voice recording. In addition, CLOVA Note will be able to recognize the words recorded in the notes more accurately. In addition, keyword search allows you to find and listen to the voice recording you needed. Next to the sharing feature, you can share the voice recording converted in the note with other members. By clicking the share button, a note URL is generated and you can share the URL alone very conveniently. Finally, there is ability to integrate with Zoom. By linking Zoom and CLOVA Note, when a Zoom meeting starts, CLOVA Note will automatically record the contents of the meeting and convert it to text. After this point, I have talked about the functions of Note. Next, I would like to explain the result of the CLOVA Note service that was released in Korea. CLOVA Note was released in Korea on November 19 last year with a catchphrase, "Make your every word a meaningful record. Leave the recording to CLOVA Note and just focus on the meeting." CLOVA Note was released in Korea. In the 11 months since its launch, CLOVA Note has received a total of 1 million uploads, 900,000 subscribers, and an average of 83,000 users per week in September. Based on this result, we believe that we have confirmed the possibility of launching AI technology as a standalone service in the market. Looking at the number of downloads, the increase is getting bigger and bigger, which is very encouraging. Now, I would like to introduce the technology we are applying to improve the recognition performance of CLOVA Note. There are two major speech recognition technologies required for the CLOVA Note. The first is speech recognition to understand the contents of the speech, and second is speaker diarization or clustering to know who spoke when. As you know, in a conference, multiple attendees freely speak what they want to say. E2E, which is strong in free speech, is an appropriate service for this task. However, depending on the domain, proper nouns such as names of people and organizations, as well as technical terms, are often used. This is a challenge even for E2E with its free speech advantage. In the beginning of the presentation, I mentioned that one of the challenges of current E2E speech recognition is that it requires a large amount of training data. I'd like to introduce a method to solve this problem: self-supervised learning. Self-supervised learning is a model learning method that uses a large amount of unlabeled audio data. Again, for E2E speech recognition, a massive amount of data is required. Moreover, the massive amount of data includes not only the speech but also the correct labels transcribed by human listeners. Therefore, the construction of the data will take an enormous amount of time and money and will be a major bottleneck. On the other hand, audio data without correct label is relatively easy to obtain. Therefore, it will be a wow if we could train a speech recognition model on unlabeled data. Self-supervised learning is what makes this wow experience possible. Self-supervised learning can be roughly divided into two stages: pre-training and fine-tuning. Pre-training is a stage of learning with unlabeled data and is a method of collecting data with similar characteristics and performing clustering. In fine-tuning, we learn the mapping relationship between the levels of the clustering data and the pre-training model. Here are some pictures of various food. Let's assume that we want to train a model to separate these pictures. The first step is to group the many unlabeled photos into clusters that have similar characteristics. Since there are no labels, we do not know what the names of each cluster is, such as hamburger or coffee, but only whether they are similar. When clustering is done in pre-training, cosine similarity is calculated as a loss, and the features of the samples are compared so that the different features become distant from each other and similar features become close to each other. This is called contrastive learning. For instance, as you can see in the screenshot, if you have a photo of a training sample, you can calculate the cosine similarity between each cluster, and as a result, the cluster named HH has the highest similarity. So it is classified as shown in screenshot. This process is repeated for all the samples. As a result, when the pre-training is over, the samples are clustered as shown in the screen. This way, we can utilize a huge amount of unlabeled data for model training. Based on the result of pre-training, we use the labeled data to learn what kind of label each cluster has using CTC laws. This is called fine-tuning. According to the Web2 2.0 paper published in 2020, we were able to outperform the existing sorter performance by using unlabeled data, as you can see in this table. In the CLOVA Note, the self-supervised method was also applied, resulting in a relative improvement of about 30%. Next, I will share the keyword boosting for improving the recognition rate of proper nouns and technical terms. Considering the nature of CLOVA Note, which is used for lectures, interviews, conferences, it is expected there will be a lot of proper nouns and jargons. For speech recognition, these proper nouns and technical terms are more difficult to recognize accurately because they are less frequent than common nouns with similar pronunciation. In notes, if proper nouns and technical terms are not recognized accurately, the user's perceived physical performance will deteriorate relatively significantly. In order to recognize this accurately, we utilize user memo. Since memos are used by users to summarize very important information during recording, it can be assumed that user memos have a high correlation with the contents of the recording. First, we'll perform morphological analysis on the user memo text. As is time, romanized words, nouns, etc. are extracted, and the TF-IDF score is calculated for the extracted words. The TF-IDF indicates the informativeness of the words, so a word with a high TF-IDF can be assumed to be an important word that represents a particular note. When decoding, we give weight to these important words so that they will be recognized better. Let's look at an example of how keyword boost can improve speech recognition. Given a user memo like this, the words parsed by morphological analysis are upload, fail, TTS, confirm, need. At this time, if we select the keyword that are important vocabulary by TF-IDF score, we can get upload, fail, TTS, etc. If you boost them, you can see that what was misrecognized as self, fitness, and ticket scout. In the example, I now recognize a fail, TTS, count, respectively, correctly. Lastly, I'd like to talk about speaker diarization. In environments where multiple people are speaking, such as interviews and meetings, it is necessary to separate the speakers. Therefore, it can be said that speaker separation is essential for the CLOVA Note service as well. To be precise, it is called speaker diarization, and it means determining whether the speaker of which segment matches the preceding or following segment for a given speech from various segments. In this example, hello, nice to meet you, and good to see you are considered to be different speakers and assign different speaker labels. Since diarization is also a form of speaker separation, we will refer to it as speaker diarization from now on for convenience. To explain the speaker diarization process in detail, the speech signal is cut with EPD and speaker vectors extracted for each segment. This is then compared with adjacent speaker vectors to determine if they are the same speaker. And clustering is performed. As mentioned earlier, in self-supervised learning, contested learning is applied to improve the clustering performance by learning to make similar examples closer together and different examples further apart. In this way, we aim to improve the clustering performance. We, the CLOVA speech team, have improved the speaker diarization model in this way and have achieved an excellent speaker separation performance of 3rd place in the world in Die Hard 3 Challenge, an international conference. As mentioned above, we, the CLOVA speech team, will continue to do our best to improve the speech recognition and speaker diarization performance through various technological developments and to provide the CLOVA Note service. We are looking forward to releasing the CLOVA Note service in Japan as well, and I hope to see you all again as soon as possible. I look forward to seeing you all again. Kida will continue with his presentation.
Well, my name is Kida. I'm going to make a presentation of the second half. Let me introduce myself. I am a manager of the LINE speech team, which is developing the R&D of the speech recognition technology. I used to work for Toshiba and Yahoo Japan in the speech recognition area, and I came to LINE last year. Thank you very much for having me. In my part, I'm going to talk about the high-speed end-to-end speech recognition that we are working on right now. As explained in Hyosuke-san's part, the end-to-end speech recognition is a very appealing technology, but does it work good in every aspect? That's not true. High accuracy end-to-end model, after reading the all sound signals, recognition starts. So it takes time to provide the recognition results. Here is a simple example.
Highway and freeway mean the same thing.
Yes, like this. After sound ends and then get the result, there is a pause or time in between. So this time is called latency. If latency is big, it's not good for the real-time subtitle or dialogue applications. So latency gets longer when speech is longer. So it is a serious problem when we have to process long speech. Well, why speech recognition end-to-end has the high latency? I will explain. So this is a typical model for end-to-end speech recognition, transformer model. So I'm going to use this to explain. And one of the root cause of the latency is the self-attention process in the encoder. When it calculates characteristics of a certain time, it refers input speech as a whole. So on this diagram, the second from the left, it's trying to calculate the time. At that time, it looks at the all information surrounding it. So this is a reason for starting recognition after reading the whole speech signals. Latency can be reduced by calculating self-attention. There are many proposals of that. So each of them limits the range of self-attention calculation as an approach. Here, I explain chunk-based decoding. In this method, we store input sound consecutively into the fixed length chunk. When the chunk is filled, self-attention calculation is done by using the range of the sound, and it goes on to the recorder. So, result is not complete, but by repeating this process, we can have the recognition result without lagging behind the sound. And latency is reduced as a result of that. So there is a concern about the latency due to this approximation. Yes, if the chunk gets shorter, the accuracy is worse. So in order to balance it, accuracy and latency, we need to adjust the chunk size, or try and error must be done for model structure or algorithm. Next, the second root cause for the latency. That is this part, decoder. So when transformer decoder receives the characteristics from encoder, it outputs a recognition result from the top one by one. So this is highway, and then decoder thinks the highway. And if a highway is output, then by using this fact, it outputs the second word. So this kind of auto-regression recognition is natural to human, but we cannot process it as a whole, and it causes the latency because it takes time. And recently, people pay attention to non-autoregressive recognition. In this approach, decoding processes will be done in parallel and not the sequential. Every word will be processed as a whole. So we use the self-attention on the encoder. It is taking time, but because of this parallelism, the latency can be very, very small. but it does not use the information about what word was output before. So accuracy-wise, it is not comparable to the autoregressive model. So we propose a new method recently, and it brought about very good results. So I would like to introduce this non-autoregressive ASR today. So base model for our approach is not the transformer model, it's CTC. And this model can output all results in parallel. That point is the same. So CTC model structure, there are multiple encoder layers and one decoder layer. In order to learn this model, we need to prepare the speech and the transcription in text, and we try to minimize an error between models, prediction text, and the transcription of the text. By learning the parameter of this model. So this is the model learning generally. And error information, as you can see here, stays strong in the area of the output, but it becomes weaker in input layer. So dark color means strength of information. We cannot make encoder which is close to the input layer learn parameters so that it would help speech recognition. So we thought this was the point for improvement. And we made the proposal. This is the InterCTC that is published by NAVER. In this model, we branch the network in the middle of encoder, and it will be connected to decoder. This decoder on the right-hand side shares a parameter with this decoder on the left. So by learning this network arrangement, error will reach the input layer while keeping strong information through subnetwork. So we aim to extract helpful characteristics for speech recognition from areas which is close to the entrance of network. But for recognition, subnetwork is not used. We do just a normal calculation, so it is too much, maybe. And here is a further improvement. Line researcher proposed self-conditional CTC. In this model, we make subnet recognize the model, and at the posterior probability distribution to next layer input, next encoder input. So this yellow arrow is coming back to the left-hand side layer. By doing so, it is conditioned to the prediction result at subnetwork and make a prediction for the final layer. To put it simple, by squeezing down the candidates using on the right-hand network, we thought we can get higher accuracy by this approach in this model. And here's a difference from the InterCTC. When it does recognition, it uses subnetwork, and then there is no mismatching of behavior. Well, let me explain the experiment result. In this table, there are comparisons of speech recognition accuracy and speed against multiple benchmark sets, including English and Japanese. Under the dotted line, there are comparison of non-autoregressive speech recognition, and CTC on top of is the baseline. When we have a large number of speed up, recognition speed is high, and the numbers of the right hand shows the error rate. Smaller number is better. So this says NAR. We have this QCell method. So self-conditioned CPC is the fastest. And to all benchmark set, it shows the best result. So we could get a very good result, we think. And we will continue this research and utilize our insight for product development. Let's change the subject and talk about the service operation utilization end-to-end model. In web service such as AiCall, speech recognition requests come to the server in multi-parallel way simultaneously. So we need to return the result to each request with shorter latency, but in end-to-end model, it is not so easy. So in order to have high accuracy in the end-to-end speech recognition, we need to use large model. As hardware, we need to use GPU. But when we process requests sequentially, we cannot optimize GPU performance very well. So here is an example. This diagram shows that A, B, and C. 3 speeches arrive the server at the same time. Each speech consists of multiple chunks. So there are 2 slots on GPU that can process chunks. If scheduling will allocate the first come request to the first slot, then GPU time resources will be used like this. So sequentially, the slot will be allocated to the chunk. When request comes in multi-parallel, then latency will become bigger and bigger. We cannot use it for the services. When we use the model, which keeps decode intermediate state, we need to evacuate information from GPU or load them again. So after C1 process, we need to switch to A1 and then move back to C1. So C1 intermediate state should be evacuated from GPU, and then we have to put it back. So this process causes the longer latency. So we are collaborating with the world-known GPU vendor, NVIDIA, and trying to find a way to use GPU efficiently. For example, if we use a Triton inference server of NVIDIA, we can reduce the latency a lot. Triton Inference Server is a framework to build the server which infer ML model with high speed by using GPU. So, let me tell you how we can solve the problem that we mentioned by using Triton. When we use Triton, we can easily customize GPU scheduling. For example, one request comes in, the C1, but process will not start it immediately. We can customize it so it can wait until all slots will be filled. And then A1 comes. Then we make 2 batches, and then GPU will do the process for those two. And we can bring down the latency. For immediate state evacuation or frequent load problem, we will make a slot remember request ID which is allocated and make it occupy the slot until request chunk process finishes. By doing so, we can control to reduce the whole latency. That's possible. By using Triton, it is possible to have the kind of a control if we just rewrite the configuration file. Finally, I want to talk about LINE NAVER speech team's accomplishment in this year. There are two top conferences, ICAP, SSB, and the InterSpeech. And in this year, LINE NAVER speech team published 9 papers for each conference respectively. It is not comparable to Google or Microsoft, but our presence in East Asia certainly increases. So we would like to continue to work on the thesis by having joint research with the universities. Now I would like to conclude this session. So in the first half of this session, we introduced the new speech recognition service, CLOVA Note. Please take the press release and then try it yourself. And in the second half, I talked about how we can realize a faster end-to-end speech recognition and how we can use GPU efficiently by using NVIDIA Triton. And finally, we are making efforts to continue to have more innovations. So please keep watching how speech recognition technology will evolve in the future. Now I want to conclude this session. Thank you very much.